So in this video I'm looking at this question in our week 5 tutorial on the Dynamic Systems and Control B subject at UTS, running in the autumn 2026 session. Here we've been told that we have to use MATLAB to create a script that allows us to find the natural frequencies and shapes of a cantilever beam with a rectangular cross-section with the parameters given in the table below. You'll notice that the parameters here are generalized. They do not include the width and depth of the rectangular cross-section beam. We expect you to be able to make use of some tool to determine those based on the inertia and the cross-sectional area. The load, or the beam cross-section, the vibration shape that we're interested in is in the vertical direction. So we're giving I for that direction rather than for the, let's say, the orthogonal direction to that. We're asked to use MATLAB to compare, or to, two beam elements to generate a solution, and compare this with SolidWorks, for example, or another finite element package. Could be Abaqus, could be anything else. Now, it's a bit tricky in these finite element solvers to specify solutions with only two beam elements. MATLAB's a bit unique in that respect. Now, I'm not going to solve the problem in MATLAB. I'm going to jump ahead essentially to the solution. So when you get through this week's tutorial and into the solutions at the end, we'll share with you a script that we've created. Actually, if I just go back to the tutorial, I should show the full description, which includes the mass and stiffness matrices for this beam element in the shape. Using the shape functions, we're able to solve for the frequencies. Okay, so the MATLAB script that's available to download and that we'll work through in the session essentially builds this solution. Look, you can here see that we've defined the material properties, so that's the density in kilograms per meter squared. We've got the area for the section, and I've given the inertia here. Young's modulus 210 gigapascals, and the length of these two elements, L1, which is a half of the overall length of the beam, and clearly 4 degrees of freedom in this solution. So we build the mass and stiffness matrices for the system as given here, and then we can invert and solve. And if I run this script, you'll see that we get 4 solutions for this 4 degree of freedom system, 4 resonant frequencies. They're not organised in ascending order of frequency. Actually, they are in descending order. So we've got 622 Hertz, 214 Hertz, 63.4 Hertz, taking into account obviously this, and 10 Hertz. 10 Hertz is the first bending mode for the beam, as predicted by MATLAB. So let's have a look at how you can model those sorts of problems in SolidWorks to begin with. So hopefully you're all pretty expert in the use of SolidWorks. We can quickly put a rectangular cross-section. Now, I said that we're not giving you the depth and width of the beam, but we've given you the area, and we've given you the second moment of area, or the inertia, 1.125 times 10 to the minus 10. So of course we can divide this essentially. A is equal to B times D, so if we divide I by A, which is this one here, then we get D squared over 12, and we can then take the square root of that value times 12 to get D, which is 0.03. Divide the area by D, gets us B, which is 0.05, and actually that's me looking at doing dB squared to look at the in-plane second moment of area. But I already knew, because I set the question, that the width was 50 and the depth was 3. But you can reverse calculate those here, and I've used B and D here to produce the area and to produce BD cubed over 12. That's a mistake there. That should be BD cubed over 12. Okay, so long story short, 50 by 3. So let's just do that. And this is modelling in millimetres. 3 here. Right. Exit sketch. It's 50 millimetres long. Sorry, 500 millimetres long. So there's our beam. Looks sensible. Now we can go to SolidWorks Simulation, which is an add-on or add-in. Okay, so we load the add-in. We haven't yet defined a material, so we can do that. Actually, we can just go to directly define that it's in steel. We can then choose to create a new study. It's a frequency study. There's another video in my YouTube channel that we link in the subject that looks at a plexiglass plate, so it's a similar sort of problem. In this case, however, we've got a fixed end, so we will create some fixed geometry. So if I click select whether that face is fixed, fixed geometry, face 1. What else do I have? Materials, good. I can create a mesh. So I mentioned that it's a bit tricky to build a mesh that's only got 2 elements. I can make it a very coarse mesh, and we can have a look at the mesh parameters for that. So here I could, for example, define these elements to be 250 millimeters long, which would give us a small number of elements. We don't have exactly 2 elements here. I think there's perhaps 8 elements. These are in tetrahedrals. So you can see we've got one long axis along here. There's a couple of pyramidal type elements in here, so there are, I think, maybe 16 elements altogether or something like this. There's some information here for us to review that. Mesh quality plots, etc. But I should probably change the mesh. Well, you can see the details of the mesh actually. Yeah. So actually there are 22 elements. The maximum aspect ratio of 176, that's not good. We don't want aspect ratios to have big numbers. That's the ratio between the longest length of a vertex and the shortest. So typically these elements are formulated to be sort of regular shapes, brick type elements, square sides, etc., with aspect ratios that should be less than 10, generally speaking. So this is not a good quality mesh. So we delete this mesh, and we can create a new mesh that is going to be considerably better with, let's say, 5mm sort of maximum length, and you'll see that that mesh there is created. Typically we might want to have 2 elements through the shortest dimension, which would be there, but this is a tetrahedral element mesh, so we'll get a pretty good result with this mesh just the way it is. And I can run the study. Actually, I'll cancel that because I also want to define some properties for the study, which are here. So I also want to specify that I would like 25 frequencies rather than just 5. And SolidWorks, in SolidWorks I need to delete them. I need to delete my results before I rerun a new study. So now I can run that study, and it's going to, you can see it's going to take a bit longer to solve, but it's pretty quick, even for a small number of elements, even on not a particularly high performance PC, as is the case for me. And I've got the first mode shape frequency of 10.123 Hertz from SolidWorks with, say, a kind of decent mesh, and I can animate that very nicely here. and I can export those animations to a folder, if I can spell properly. Okay, and similarly I can see the second mode. Now the third mode here in SolidWorks is an out of plane, or I should say in plane mode, I beg your pardon, so that's now vibrating in the plane of the beam, if you like. So that 166.6 Hertz is for that particular shape. That's our 1, 2, 3, third bending mode. That's a torsional mode. That's the fourth bending mode. So that frequency is 384. So we're collecting these frequencies to compare with MATLAB 177.6. So you've got to watch out for those sort of other frequencies that are for shapes that we're not predicting in MATLAB in the comparison. And again, if I go to the results or the solutions file, so I'm kind of jumping ahead, go back to the canvas. Here are those predictions from SolidWorks, which I've just extracted. So I noted those down while I was typing, so you can see those. Now they'll vary a little bit depending upon exactly how we build a model. That one seems to vary quite a lot more this time, if I got that correct from SolidWorks. This just generally says Finite Element Analysis, and MATLAB gives us these frequencies. So we're predicting quite a different result. In fact, I just should probably check what's happening in SolidWorks there. Did I get the right mode? That's 348. I noted that down wrongly there, so that was a typo. I'm glad I checked. Easy to do. That looks more like it. Yeah, about 348. Now MATLAB over predicts quite significantly, apparently. In that respect, all of these tools are making an estimate. None of them are correct. All models are wrong. Some models are useful. Okay, so you have to remember that. Now that's SolidWorks. And you can see I have frequencies going increasingly all the way up to very high frequencies. That's a high order torsional mode, a higher order torsional mode. So from a testing standpoint, obviously I would need very fine resolution of my degrees of freedom, my measurement positions, if I was going to be able to extract these frequencies. Not only that, I would need to be able to excite the structure at a relatively high frequency. This is not an enormous frequency, 3.8 kilohertz. We should be able to achieve that with an excitation using a modal impact hammer or a small shaker. Abaqus is another option we have. This is now a, let's say, gold standard solution for model analysis, or finite element analysis I should say. So I go to this work directory, so this is where I'm going to produce and set the work directory. That's where all of the things that I'll create are going to be stored ultimately. I'm going to do a 2D planar wire-based solution with an approximate size of 1. That's twice the largest size of interest in my model. I'll just draw a straight line, put a dimension on this of 0.5. That is essentially the median axis, if you like, of my beam. That's it. That's the part. Now, I define the other things in here, so I'll call it steel. We need a density, 7,850. We need some elasticity, 210 gigapascals, 0.3 for Poissons for ductile metal. I need to specify a section. So this is a beam, we'll call it. I need a profile for that section, so this is going to be a rectangular profile. there are other types of profiles like generalized, where I can specify, like in MATLAB, just the area and the second moment of area, the inertia. But I'm going to actually specify it according to the dimensions. So this is 0.05, 0.003, we're modelling in meters. It's already given me or it's worked out that I've only got one material in my list, so I have to use that material for this section. Okay, so now I've got a section now, I can assign it to this member, this particular bit of geometry in my model, right? So then I've only got one section, it must be that one. It's a type beam that's using the material steel, and this goes turquoise to indicate that we've properly specified it. The other thing I need to do in Abaqus is to define the normal direction to that particular cross section. Right, so that is thinking that that would be normal to the cross section. If I look at it in this orientation, you can see that's sensible. I'm subsequently going to apply. Yeah, so that's tangent. That's normal, and this is the one in the two directions based on that profile that I created. Finished there. That's okay, and I can actually now, just to double check, for example, I can turn on, I want to render the beam profiles with a scale factor of 1, and then you can see very nicely that the beam is as I expect. Now in Abaqus we have to assemble our parts into an assembly, so that's completed. I'm essentially working through this series of steps here to build my model, and this is the process of building a finite element model. Define a part, create a property, build an assembly, create a step. That's essentially what's going to happen. I can then do interactions, so if there are multiple parts there can be contact, I can apply loads. In a frequency analysis there are no loads normally, it's like a free vibration question or problem. I can then assign a mesh, and there are some other steps that I may or may not specify something in. Ultimately I can create a job and submit it to the solver. I'm at the step stage. This is going to be a frequency step, and here I take linear perturbation, choose frequency, continue. I can give it a description if I wish. This is where I would specify how many frequencies I want to extract, how many eigenvalues. So I'm going to make it 25 to be consistent with what we did in SolidWorks. Skipping interactions, there are no second parts. I can define some things with respect to that if I'm doing different types of solutions. This is a very general, high-power system. I don't need all of the capabilities that exist within Abaqus to solve this kind of a problem, but I do need a boundary condition that's fixed. It's going to be this type, symmetry, anti-symmetry, encastra. That is the one that we will choose to be specified at this point, and it's going to fix that point in all three translations and all three rotations. They are set to 0, and you can see, as we would expect to see when we apply that kind of a boundary condition, it's consistent with what we saw in SolidWorks. Nothing can move. You'll notice that because I'm now in an assembly view, my beam profiles are not rendered, but I can apply that. And that's essentially showing me again what's happening with this beam. It's optional really whether we need it. Meshing. Okay, I get that warning because I'm meshing at the part level, not the assembly. Now I've gone back to part and the beam profile is being rendered here. First thing that I do is I specify seeds, so I can now do something that's consistent with the problem that's been specified with the two elements. And if I turn off the beam rendering there, you can see the seeds now that have been created, where it's going to target to build a mesh with nodes at these locations. That's because I've specified them to be approximately or exactly half of the overall length. Okay, so then I assign the mesh. Okay to mesh the part, yes. And it goes again to this turquoise colour to indicate that it's meshed. There are some other things in here that I can have a look at, mesh controls. I can't do that for 1D systems. I can also switch between linear and quadratic order. Now this is about the way that the shape of the elements is possible to deform. We'll have a look at linear to begin with, but then I will come back in and make a new model. Actually, I will rename this model here beam linear at this stage. Right, so we've got a mesh, it's linear elements. I'll go to the job, we shall create a job, beam, lim, continue. Again, I can give it a description, I can specify how much, how many processes it might use, how much memory I'm going to allow it to make use of. This is a quick, small job, so I really don't need to think about multi-threading and these sorts of features. Now if I go to the job manager, if I had multiple jobs, multiple models here and multiple jobs, these would all be listed. But the first thing that I should do is do a data check. Now this is a good idea because if I've forgotten to specify something in my model, like I haven't, for example, specified the normal direction of the cross-section down the beam, this will check for me to see if actually the job that I'm proposing to submit, based on how I've built this model, does it make sense or not. And as you can see, that's running. It's taken a few seconds and there are no errors, no warnings. There's not yet anything really in the output database, but there is an output database with something in because I get the results of the check. And so if we have a look at that in that folder that I specified as my work directory, I'm working in here. These are the files that were just created. Now you can see there are lots of various different files that are created. A message file, a data file, a status file. And there's my output database. It's relatively small at this moment, but that contains the output from this data check, which completed successfully. Now if I go back here to Abaqus, rather than hitting submit after a data check, I can just say continue. It's going to say there are some job files already that exist here. Are they okay to overwrite? Particularly it's creating a new output database. Yes, that's okay, because I know that the things that it's looking to overwrite are simply the results of the data check, which doesn't contain any actual useful information. So I will say OK, and away it goes. It continues now to solve this problem for the 25 frequencies and shapes that I've requested it to solve for. Now you will see that it does create some warnings. It tells me that there are only 6 eigenmodes available because there are no more unrestrained degrees of freedom, and that's because of the way that I've built the model with only these 2 elements. So I'll have a look at what that means. When the job finishes, if we expand here, we can see actually it already has finished. If I right click, I can go to the results, but before I do that, I think I'll just copy the model and I'll set up another job that's going to run while we're having a look at the results. In this job, I'm going to go to the mesh. So you'll see that it's underlined, which means that that's what I'm working on currently. So this first problem has already been solved. I've got a solution, but now I'm working on this copy, and I can change things specific to this copy. I said I wanted to change these geometric order of this. Right, so that's now got a different geometric order, i.e. quadratic. Now I can create a new job for this using that model. Right, so that's my original model, this is my previous model. Beam quad. Continue. Okay, now I've got these 2 models, right? One is completed, one is not yet run. Right click that and I'll just submit it directly this time, and that will be running while I'm having a look at the results from this job. So now it moves to the visualization module over here. The model is running in the background. That's quite handy. If that's going to take 10 minutes and I'm going to spend 10 minutes looking at the results from the previous one, that's quite a useful thing to be able to do. It doesn't take 10 minutes, it only takes a few seconds. But nevertheless, I can now come in here and have a look at the results from the linear element type result from before. These multiple plot states are useful. It shows me the deformed model against the undeformed model. I can have a look at that on an isometric view. I can again, for this particular module, choose to show the rendered beam profiles, right, and now I can animate. I know I'm moving through all of this quite quickly. This is not necessarily a training video on how to use Abaqus. I'm just highlighting the differences between these for SolidWorks and Abaqus, and there's my very nicely looking animated beam. I can, from here, save as, like I did before, an AVI. If I want to export this here, Abaqus, first bending, and generally speaking it would also be sensible to include the frequency. So that's the thing that we haven't talked about yet, but this is 9.1 Hertz in this case. Now this is important. I'll call it 9.09 Hertz because it's not what we were expecting, right? It's not close to 10.1 or well, my solutions from Abaqus 10.03 I got from MATLAB. Yes, so it's quite a lot less, and that's because I've used this linear element type. I probably should have included that in the name here as well, so we know the difference, right? So that's now extracting that. Now if I go back to my model file, go to this one, open the results for this. You see I've got now two databases open simultaneously. This one's highlighted, this is the one I'm looking at. I can export these. You can see I've got more degrees of freedom for this solution. Show that one again. Visualize that. And importantly now, 10.04. So for Abaqus with a quadratic element type, I get 9.0 something for that one. Abaqus quadratic 10.042. So now we're in very close agreement. SolidWorks is a coarser estimate. Abaqus produces a very nice comparison with the answer from MATLAB 10.03 for this beam type with a quadratic element type. And I can scroll down. You see, however, I mean, this is still, remember, only a 2-element solution here. This is not like SolidWorks with sort of 5,500 elements. It is literally 2 beam elements, but because the beam elements are formulated taking into account how a beam behaves in reality, these are this is what I get to see, these, and so you can see similarly, okay, 66.5, so we were doing the comparison, 66.5, that's nearly, it's close, 223.56, this is not a great solution when we get to these higher spatial resolution shapes are clearly not able to be represented, with 2 elements. Yeah, so if I actually turn off the ODB beam rendering, you can see that we actually get the resolution, sort of the spatial resolution. That looks more like a bending mode, higher order bending mode. That's interestingly a longitudinal mode at 2.5 kilohertz. That's another longitudinal mode, like the second longitudinal bending mode. It's quite interesting to visualize the symbols on there as that's deformed. So you can see how that is at that higher frequency. So at this lower frequency, it's moving longitudinally back and forth, but so all of the material is extending in phase with the rest of the material. It's perhaps even better to just turn off. So now you can see the direction of deformation. If you look at the direction of deformation here, and if I actually probably slow it down, look how these are out of phase with respect to each other. So this mode is a 2 DOF mode where we're out of phase, in anti-phase. these two elements, and clearly it's a much higher frequency, 7.9 kilohertz versus 2.6 kilohertz, and so on. Okay, so actually we should turn this one off, and you can see those additional frequencies. Now, to get better frequency estimates with Abaqus, I should still have some more elements than I have. So if I copy that model and have it much finer, switch the context, close this one, switch the context, and now it's going to jump back to meshing. Go back to the seeds, make those say 0.05, so I have 10 seeds. It gives me a warning that that's going to result in my mesh being deleted. Now I'm going to have 10 elements along here. Mesh the part again. It's happy once more. Build a job. Beam, quad, fine. Okay. Run the job. Take a bit longer. Monitor it as it goes. Check that there are no errors, warnings, etc. This time I can have my 25 eigenmodes without any warnings, because I have enough spatial resolution to be able to animate those or represent those in the results. Okay, so here we go. We're still animating in the same way as before. I can again show these if I wish. And 10.03 to compare directly with MATLAB. Perfect, beautiful, very nice solution. Okay, let's go back. I can actually just jump through to the next. No, that's going frame by frame. No, I need to expand here into these steps, in fact, and do it this way. Okay, that's the second mode, 62.83. Let's have a look. 63.4, so some difference. 176. Okay, but that's very close agreement with SolidWorks. You can see there's some difference with MATLAB. MATLAB is estimating, it's only using 2 elements. Third bending mode, 345.5, so that's now in very close agreement with this result from SolidWorks, and also, importantly, with the analytical solution. So you can see how we build this up, comparing the finite element, MATLAB, analytical solution. Of course, we would then now instrument or build a steel cantilever beam, try to produce a fixed boundary condition at this side, instrument it with say 10 positions or 1 accelerometer on one end, and strike it in 10 locations with an impact hammer, and physically determine these resonant frequencies for such a structure. And then you can see here how you can complete this kind of a solution. You see now that these longitudinal mode frequencies are in a different position relative to the other bending modes. See how much higher we got in with the bending modes compared with the first resonant frequency. I have to turn off the rendering to be able to show the material deformations as these shapes present themselves. Now you can see we get an arrow at each of the at the nodes. We've got 11 nodes now, whereas before we only had 2, so we get these arrows. And that's our higher order bending modes. And at some point we start to see some spatial aliasing. That's our second longitudinal mode there now, with a nodal line partway along. and so on. Okay. Third longitudinal bending mode with 2 nodes. Fourth longitudinal bending mode, longitudinal mode. And so on. That's a long video, over 35 minutes, but I hope that it has given you some interesting insights as to the differences between SolidWorks, between MATLAB, between Abaqus, for finite element analysis and simulation of these frequencies, to be able to allow us to understand how these systems vibrate such that we can specify a sensible experimental campaign. And of course, when our problems get more complicated than rectangular cross-section beams, MATLAB cannot help us anymore. It's very difficult to model in MATLAB with finite element from first principles, but we can model these more complicated things either in Abaqus. Abaqus is somewhere in between. You can see how I can model things in Abaqus. SolidWorks, however, gives us very nice capability. It's a CAD package with a simulation add-on, however it doesn't predict as accurately as Abaqus does the frequencies of the mode shapes. I hope that's been a good, nevertheless long but informative video. I hope it's of use to not only candidates studying Dynamic Systems Control B at UTS, but also to other people generally interested in finite element analysis. My name is Associate Professor Ben Holcomb. I'm from the School of Mechanical and Mechatronic Engineering in the Faculty of Engineering and IT at UTS. Thanks for watching. Goodbye.